limited. A current CPU is typically not clocked above 4 gigahertz. The industry sidestepped that problem with introducing multiple cores per die, but following Amdahl's law, this parallelism also has limitations, so having more than 32 cores per CPU maybe doesn't make too much sense. Now, the question is how we can still profit from the increasing number of transistors, and the specialization of silicon seemed to be a new promising way to go. Specialization means accelerators, that means not generic CPUs. With that, the industry starts to design architectures with a specific class of application or computation in mind. Next slide, please. So, what are the silicon alternatives for the rapid enterprise-ready specialization of silicon? On the left side of that picture, you see the good old CPU. That one is not specialized at all, but very flexible with limited efficiency. That's where we started from. The next to the right is the GPU. It is efficient at processing the same set of operations in parallel. So it's simply a single instruction, multiple data machine. It has a well-defined instruction set and a fixed word size. Further to the right, we find the field programmable gate array, the FPGA, which is effective at processing the same or different operations in parallel. So it is a machine which shows multiple instructions on multiple data. It does not have a predefined instruction set, though, or it doesn't have a fixed data width. Far right out, we have something which is even more efficient per silicon, which is the ASIC. And in France, that system is not programmable, that architecture is not programmable, and with that, we are not talking about this today. Next slide, please. So, what is the goal of the project of CLOUDFPGA? The main goal is to deploy FPGAs at very large scale in hyperscale data centers. Very large scale doesn't mean hundreds of FPGAs, but thousands to 10,000s of them within one data center. And we want to provide those FPGAs in a cloud environment. Cloud environments comes with specific requirements, which I have listed on the left side. I do not read them all out, but I will give a summary. Besides of flexibility, security, and on-demand availability, it's all about the economics of scale. Next slide, please. With that, so we are not talking about FPGAs in a server box. We looked around at the start of the project, and the densest system we could find was the one depicted here on the right side. This system is not going to work in a cloud data center, since if you, for example, wanted to make available 1,000 FPGAs, we would need 12 racks for that, where we would spend 10 million on it. And that's because we would have high-end FPGAs, we would have many CPUs, and besides of that, we would need lots of energy to drive such a system. Next slide, please. So CLOUDFPGA in a few words. What do we want to do? We want to break the master-slave connection between CPU and FPGA. We want, in principle, standalone FPGA operations. We want to disaggregate the FPGA from the server and let the FPGA-based computing scale independently of the number of CPUs. So we want to let them come and go, power them on and off quickly as far as we need them currently within our data center. So with that premises, we must have the FPGA network attached, and the network must be easily configurable to connect a bunch of FPGAs using any preferred topology. Another requirement which falls out of cloud deployment is that high-end equipment is not compatible. We prefer mid-range FPGAs. Why do we prefer mid-range and not high-end? The simple reason is that they give us about 70% of the performance at 10% of its costs. On the right side, we tried to bring up an analogy to our approach, how to make a parcel delivery service more efficient. One idea from a company which is selling cars is to replace the driver, we call him Mr. CPU, by an autonomous car and a delivery robot for the last 20 meters. That may work, but the savings with that approach would be limited. Another maybe better idea from a company which is not selling cars is to let the man not be laid off, but to fly Zeppelin, which would be much more fun than to be laid off, and fly the Zeppelin over the city of delivery, and then send drones to deliver the parcels to the destination. That may limit the size of the parcels, but for maybe 90% of the size of parcels, that idea would be sufficient. And for the rest of the 10%, we could ask this sender to disassemble and send multiple small packets. Next slide, please. So what we want is to have FPGAs becoming first-class citizens in the cloud. On the left side, you see what most of providers and vendors are doing these days if they deploy FPGAs. It's a CPU-centric deployment where the FPGA is attached to CPU via a local I/O bus system that might be advanced, like OpenCopy with cache coherence and so on. But what we want to do is depicted on the right side. We want to make the FPGA a peer processor and connect them directly to the data center network. For that, FPGAs can talk to each other, and if they really want, even to the CPU. With that approach, the FPGA scaling becomes independent, and a user can build arbitrary clusters of FPGAs without carrying along idling CPUs. Next slide, please. So with that, we want to share our vision on how to do the integration. And first of all, we wanted to build the densest platform possible. So we squeezed as many FPGAs into a chassis as possible and connect them via Ethernet, ending up with 64 FPGAs per chassis. This 2U box fits 16 times into rack. With that, we have a density of 1000 FPGAs per rack. We could, of course, also mix that FPGAs with CPU servers, but we don't want to do that because we would have to change the overall approach, how to integrate systems, and we would touch upon the current infrastructure of a data center. With that, this little blue man would ring at your door and tell you can advance your data center without touching what you have. You just have to connect this new rack to your data center and you are all set. This is a very non-intrusive way to give FPGAs to the data center. And you see it on the far right, the data center would become a mix of hyperconverged servers here in white and FPGA racks in yellow. Next slide, please. With that idea of an infrastructure comes our cloud deployment vision. How do we fit into the cloud service model? The simplest model on the left side, number 1, is just to provide the infrastructure. So the user would here download the provided by us CLOUDFPGA development kit, developed his ideas, and rent one FPGA where he runs his application controlled by a virtual machine. More interesting is the second approach, depicted numbered as 2. We can provide a bunch of FPGAs plus one control entity to run the program. For a company which does some gene folding and wants to run its kernel on 100 GPUs, this user would just need one container with maybe one CPU and to distribute the load and then have its 100 FPGAs crunching the data. This is of course much cheaper than a FPGA CPU integrated model. Number 3 is an even larger FPGA deployment where we want to serve more value-added services like inference with pre-trained models to do surveillance, health checking, or whatever. Think of a ResNet 50 model, which is a layered architecture which nicely maps to a cascade of thousands of FPGAs. And far on the right side, that's a future, or it's an idea how we could extend the use case. It's basically deploy that infrastructure to serverless framework where individual serverless functions nicely map to individual FPGA instances. Here, a serverless data flow graph might nicely map onto a chain of FPGAs with individual programmed functionality. Next slide, please. We're moving on to the architecture and design choices, looking first at the hardware which was developed. So if the FPGA becomes a standalone node in the data center, to deploy it, we shall resemble the behavior of a normal server deployment, a bare metal or VM or container of CPUs. It shall be configured out of individual requirements, number of cores we want to have, DRAM we want to have, and number of disk amount of disk space we want to have. You ask for the cloud resource management will configure it for you and provide you finally the IP address of your system to run your program. The FPGA shall be the same. So in that case, the user shall be able to pick the FPGA resources, the amount of DRAM, the number of CLBs, the number of DSP, and the management system shall instantiate the instance and send an IP address back to make it usable. So with that, what you want to achieve is to have CPUs and FPGAs being controlled the very same way. Next slide, please. With that requirement, the team started to build such a standalone FPGA, and in principle, what they did is replacing the PCI interface of the FPGA with an integrated NIC. Then they turned the FPGA card into a standalone system by adding DRAM and replacing the expensive Ethernet transceiver with a backplane connectivity and with an ARM core, a small ARM core spanning just 150 milliwatts, being always on as a control point to manage IP addresses to allow power on, power off of the FPGA and do thermal measurements and this kind of stuff. Next slide, please. So since we do not want to pollute the network with thousands or 10,000s of these small FPGAs, each with a port at the data center, we are packing them densely. So we are packing 32 FPGAs into one slot with one Ethernet switch on it, and and that SLED fans out this the same exactly bandwidth as these 32 systems, namely 8 times 40 gigabit Ethernet. Next slide, please. So this is how the complete 2U unit looks like. We have two SLEDs within one 2U 19-inch, 19 centimeter height unit. It is water cooled, has a copper heat sink per FPGA and per switch. This is very silent and very efficient. And what you see in the far upper left is a single control point. This is a little Linux system running on a mini ITX form factor board, which is used to control the chassis. Next slide, please. Moving on to the software architecture. Next slide, please. The overall software architecture is not much different from what others are doing. Basically, we have two items to look at here. One is the light blue coded shell, which is running privilege logic, which abstracts away hardware components of the FPGA and exposes standard interfaces to the user. The dark blue is embedded, running within the shell. It is called role. It is non-privileged and it embeds users' application logic, and it's partially reconfigurable over the network, typically via a high-level synthesis. Next slide, please. Next item in software is the so-called CLOUDFPGA development kit. It is basically managing the magic between a program and the VHDL and Verilog code, which is running at the FPGA. In the end, it supports high-level synthesis, so the CLOUDFPGA user does not have to have the code in Verilog or VHDL, but can use higher-level languages like C++ and C today, and we're currently looking into Python support. Next slide, please. The third component is the so-called FPGA management core. This FPGA management core controls loading and activation of application code. So basically, it loads and starts the so-called bit file. And since we do not have a PCI bus at this FPGA card, we have to somehow find a way to feed the program into the FPGA card. And this is done via a little stripped down HTTP server running within that management core, and which is talking REST API, understanding the usual post, get, and put operations to load arrays, code, and set, read other information such as routing. This management core is not directly accessed by the user, but used by the data center resource manager. Next slide, please. With that, we come to that data center resource manager. And can you, next slide, please? And with that, we are back to that promise that we want to do something very similar to a typically CPU-based cloud deployment. And how does it work? As a user of a normal cloud, you are facing a pool of resources, which are typically processors and images, and you select a processor or a number of cores, and you select an image to run on your system, which might be Fedora, Ubuntu, or whatever Linux. And the management service of the cloud creates you an instance of it. And if you need more than just one of it, the management creates you a cluster out of n instances and deploys it for you in the data center. Next slide, please. So we want to be very similar for the FPGA data center case. So the only difference here is that we have a database of bit streams and not of images. So the bit stream becomes the image, and the instance is now a FPGA running a bit stream and not a CPU running a Linux. The user loads his or her bitstream to a central database, and the data center cloud FPGA resource manager picks the image from the database and loads it via a per SLED manager and to the local FPGA management core of the target FPGA after powering the FPGA on if it was off before. If more than one instances are needed, the data center resource manager deploys a bitstream on n FPGAs. Next slide, please. As I said earlier, all control is based on a RESTful API, which is quite handy, and which even allows a nice graphical interface, which is depicted here. You basically post an image or a group of images, and they get deployed on the hardware you want to have. And you get back your IP address or the number or a number of IP addresses if you deploy more than one bit field, or if you want to use more than one FPGA. And with that IP addresses, you are ready to use your FPGAs. Next slide, please. Now let's look into two examples of how cloud FPGAs deployments are possible within our on-premise test data center. Next slide, please. First is a very simple example where we run a hello world program with a single FPGA. The user would download the development kit to work remotely on its desktop, or would use a virtual machine within the cluster. It would set up a VPN client. It would create an OpenStack project as a private network where you would deploy its FPGA. He would develop and simulate. He would upload the bit stream to the database and would get back an image ID and would request an instance to be launched with that image ID and would get back an IP address for that image, and then you could just use that image as an FPGA running his code. Next slide, please. Now, the next example is more complex, a platform as a service example. We start with an MPI C program, which is annotated with some FPGA specific code. You see that in the upper right of that picture. And the use our own ZL MPI CC cross compiler, which produces two outputs. One is a high-level synthesis file, which gets passed to further specific processing, ending up in an FPGA bitstream, and it also spills out a C file, which gets further processed, ending up in a CPU software binary running on the single CPU we need for that program. In the end, as a one command deployment, which is depicted on the lower part of this picture, the ZL MPI run command takes an IP address of the server, the bitstream ID for the imagined 8 FPGAs, and the software binary for the CPU server, and with that you have your program running. Next slide, please. Now we look a little bit into cloud FPGA networking. Next slide, please.
Bernard, just a sec. I just want to add a comment here. So for folks who want to ask a question, feel free to just chime in the Q&A box, or even raise your hand so I can unmute you to have a lively conversation. Thank you. Sorry, Bernard, go ahead.
No problem. Okay. So this slide I wanted to put in the backup, but it happens here. Okay. You see the small water-cooled iPhone-sized switch at the right. So this is the switch per SLED. And two switches, since we have two SLEDs, are contained in one 2U unit, and they provide 10 gigabit Ethernet to each FPGA of their SLED. Again, we are talking about mid-range FPGAs, so 10 gigabit Ethernet is far enough to make them available. And as you see in the graph above, there is besides of the direct connection between the FPGA and the switch port, there is also a redundant link going from left to right, which basically allows to have FPGA still accessible if one of the two switches dies. There's more funny stuff to look at here, like additional PCI links between two FPGAs and connectors forming rings of 4 neighboring FPGAs when they can talk to each other without involving the switch. Next slide, please. Looking into the per network card communication stack, what do we have here? First of all, it is part of the shell, so it's running in privileged mode. We don't have user level networking. It's based in the shell, so it's privileged and cannot be changed by the application currently. This communication stack implements 10 gigabit Ethernet and a TCP/IP and UDP/IP stack, plus it's combining protocols like ICMP and ARP. That communication stack per FPGA can drive up to 10K connections, and it supports both active and passive connection management. It consumes 50% of the FPGA logic. Again, it's a mid-range FPGA. On a larger FPGA, it might be less than 50%. Next slide, please. Looking a little bit deeper into the networking, receive, transmit paths, what is important to know here is that the application is exposed to an asynchronous socket-like API, and both transmit and receive paths are asynchronous. That means a TCP offload or UDP offload engine receives and places data into intermediate buffers and signals reception to the application, and the application copies it by a read call. There is a performance optimization for small number of connections. If the application can consume the data immediately within the up call, there is no data copy. As you see, this architecture is ready for RDMA. It is asynchronous, and it does one data copy, which is not really necessary if you would talk RDMA and if you would have the semantics of the RDMA protocol to directly place data into application buffers and to fetch data directly from application buffers on transmit. But we need someone who would write us the IWARP or Rocky implementation on top of TCP or UDP, and we would need someone who is willing to extend the application API to speak libfabrics or libIB verbs, and feel free to contribute if you're interested. Just talk to us. Next slide, please. A little summary on the performance of that cloud of that FPGA stack. You see that the latency is quite low. The runtime for UDP between two FPGAs is 2 microseconds. For TCP is 7 microseconds, and the throughput on UDP maxes out at 1K packets, and TCP is achieving 80%. Next slide, please. Last not least, we are currently looking into integrating non-volatile memory. And the question is how to best integrate non-volatile memory. There are basically two options here. One is to use the flexible architecture of Cloud FPGA and to replace some, for example, each second FPGA card with an NVMe card running an NVMe F target. But we could also add NVMe resources per FPGA, and that's the preferred option we are currently looking into. It will be based on NVMe F over TCP, and it will allow for very dense integration up to 4 petabyte of flash per rack. And we are sure that the heat dissipation system of the Cloud FPGA drawer will be ready to handle that additional load. This option is a very trendy option since it allows FPGAs and NVM to do fancy things like data deduplication on the fly, like implementing integrated key value stores on top of NVMe and stuff like that. that's something other vendors are doing within their standalone NVMe systems. Next slide. That's a summary, and in that summary, you see the heat pipes on the system on the right side. So summary is FPGAs are eligible to become first-class citizens of the data center, and the standalone approach sets the FPGA free from the CPU. It allows large deployments of FPGAs independent of the number of servers, and it promotes the use of medium and low-cost FPGAs in the cloud. Network attachment model makes FPGAs IP addressable and scalable in data centers. Users can rent and link them in any type of technology. It opens the path to use FPGAs in large-scale applications. And this hyperscale infrastructure is integrating FPGA at the chassis level, so that makes them very nicely consumable to given data center architectures. It combines passive and active water cooling, and we think it is a key enabler to FPGAs to become plentiful in data centers. Next and final slide, please. This is on the future work. As I mentioned at the very beginning, we are planning to open source the Cloud FPGA development kit to give the research community access to the Cloud FPGA platform. We are doing that because we need help to work up the application stack at one hand. So we already have a project running on low precision and inference and auto machine learning on Cloud FPGA, but we want to see more projects like large-scale distributed applications, and we also need or would be happy to have support for more programming languages and frameworks besides of C and C++. At the other hand, we also want to work up the system stack. We want to integrate with function as a service deployments, serverless computing frameworks like Apache OpenWhisk or Knative. We want to add, and we are in the process of doing that already, but we may need help for that, composable and disaggregated storage. We want to deploy lighter and faster data center network protocols like TCP/IP, and as I mentioned before, we would like to add RDMA protocols and APIs. And besides all that, that architecture is open to expand the number of Xilinx-based modules, and is also not married to Xilinx. It could also support other FPGA vendors. And finally, we want to share the whole Cloud FPGA platform architecture design in the same way as Open Compute Platform is doing it. So we hope to spread the idea of Cloud FPGA with that measures. That's all from my side, and a little bit over time. Sorry about that. Is there any question?
I have not seen anything come through yet, Bernard. So let's give. Oh, there it is. Arnold.
Maybe this was too much material for the 30 minutes.
No, it was good. Actually, we do have a question. So hold on, please. Arnold, I'm going to go open your mic. So there you go. You can actually ask your question real time. Be good for someone else speaking other than my voice, I guess. Can you try your microphone? Arnold? Oh, there. You muted yourself. Try again. Yes. Okay, we cannot hear you. So I'll go ahead and read the question. The question that came in is, what applications have been ported to this platform? Question number one, type or class of the applications, anything you can mention?
So the biggest thing probably what we have running is the MPI suite. So we have that MPI compiler, and we can run MPI applications on top of it. And I would have to ask, maybe you can unmute him, because I have seen him as the attendee. We could ask.
Yeah, his microphone is open from my side. It's just something technical problem, I guess, on our side.
Okay. I don't know what else do we have.
Okay, so the next question is, for the application ported, have you done any comparative studies between an FPGA platform and a GPU or a CPU-based platform?
I'm not aware of that. Sorry, I have to say I'm not the most involved person in that project, and I would like to have somebody else picking up from the team because I see them as attendees. So maybe we can ask Francois, or we can ask, yeah.
Okay, yeah. Sorry, hold on. What is the name you said?
Francois Abel. Francois.
Okay, let's see. Yeah, I see him. Okay, there. So Francois is unmuted now. So Francois, if you like to chime in, the question is what applications have been ported, and if there was any comparative studies done using an GPU or CPU-based platform, and how does it work when compared to an FPGA-based platform?
Yeah, so hello everyone. No, so as Bernard said, this has been driven by a very small team, and we rely on basically numbers from Xilinx when we compare to video transcoding and AI inference. The reason why we want to open source that is to have all of this work done, because yeah, we are like a handful of people, so we have not done that work.
Okay, sounds good.
You found those numbers in the FPGA community. This is a pure system effort until now.
Okay, thank you for that. Any other questions from the audience? All right, thank you, Bernard. It is a lot of information, good one. So, hold on, I think something came in. Here, is there any type of application not suitable for this type of infrastructure?
Not suitable, that's difficult. Okay, you have to think of it. This is like a server. You don't have to know that as an FPGA at the other hand. You have now a TCP/IP stack in hardware, so people don't like it. But if it's in hardware, we have latency close to RDMA. So you talk to an FPGA like you would be talking to a server. So now you can dream of anything else. That's why we go after serverless computing. We think a lot like Lambda function from AWS or Cloud Function from IBM. This is what we think is could be suitable if you operate a data center, of course.
All right, thank you, Bernard. Thank you, Francois. Those were the questions for you today. So I'm going to move to the next presentation in interest of time. The next speaker we have is going to talk about OFI and how to enhance it for invoking acceleration capabilities on an integrated networking FPGA platform. Venkata Krishnan is going to be joined along with two other speakers, Mike and Olivier. Venkata Krishnan interest is in microprocessor architecture and accelerators in networking. He has a BTech from IIT Madras, quite reputable, along with a PhD from University of Illinois at Urbana-Champaign in computer science. Prior to joining Intel, he had held positions in Dolphin Interconnect as a CTO, research scientist at DE Shaw, and also as a fellow at AMD. It is my pleasure to welcome Venkata here. Venkata, go ahead, give a try to your microphone.
Thank you.